Simple gas laws. So there's 4 basic properties or variables for gases: pressure, volume, temperature, and amount. The symbols are listed there. Pressure is capital P, volume is capital V, temperature is capital T, all very nice. Amount is moles. Why is it an M? Yeah, that's a good question. I think, we use M's so much. We can't use M because people are going to get it confused with molarity or with meters or something, so it's M. Sorry. You can deal with it, though. It's like half of an M. Does that make you feel any better? These properties are related. If one changes, another changes. And so we're going to look at a little bit of history that I'm not going to quiz you on the history of it. But we're going to look at some scientists who discovered the simple gas laws. And the simple gas laws describe the relationship between pairs of these properties. So the first one we're going to look at is called Boyle's law. Robert Boyle lived back in the 1600s. And he studied the relationship between the volume of a gas and its pressure. So he took a J-shaped tube, and he would put a gas in this short end and seal it with a stopper. And then there's mercury in here to contain the gas and also allow him to measure the pressure. So it's a very simple manometer. And so we can look here at the difference between atmospheric pressure and the gas pressure inside, so we can figure out the pressure of this gas. Then he would change the pressure of the gas by adding more mercury to the tube. So you add more mercury here, it presses down more, and it causes the volume of the gas to decrease. And so he changed the pressure. He's measuring this distance here so he can measure the pressure of the gas, and then he's looking at the volume of the gas as well. And so he looked at the relationship. He found that when you increase the pressure, the volume decreases. So this is an example of a Boyle's law graph. In science, we graph the controlled variable on the x-axis. So he was controlling the pressure, and then he was measuring the volume. And so we see that as you increase pressure, the volume of a gas will go down. And that makes sense, because if you think about like a balloon, if you squeeze it on all sides, it's going to get smaller, right? When you put pressure on it, you're going to compress the gas. So Boyle's law can be expressed this way, as the volume is proportional to 1 over the pressure. This is an inverse relationship, meaning that when one goes up, the other goes down. And where we say constant T and N, that's important. That means that the temperature is not changing and the amount of gas is not changing. Because if either of those changes, then this relationship is not going to work.
Are you going to be giving us problems that like all of the stuff is changed?
Yes, there will be problems later where lots of things are changing. Yeah, fabulous. I love gas laws. So the graph of volume versus pressure is curved. Curved lines are difficult to deal with, but if we graph volume versus 1 over pressure, we get a straight line. And I'll show you that in just a minute. So as pressure increases, the volume decreases by the same factor. Another way to state that is the pressure times the volume for a given sample at a given temperature is going to be a constant. If you change the pressure, the volume's going to change, and you multiply those together, you're going to get the same number that you started with. Another way to express that is this way, and this is what you should memorize. P1V1 equals P2V2. Always makes me want to say R2D2. P1V1 equals P2V2. So here are those graphs. Here's volume versus pressure. It's a curve. If we graph volume versus the reciprocal of the pressure, 1 over the pressure, we get a nice straight line. And it has an intercept of 0 and a slope of 1. And so that allows us to predict what's going to happen when we change the pressure or change the volume of a gas. Here's another illustration. So here we have a 1-liter container, and here's a pressure gauge, and it's telling us the pressure is 1 atmosphere. This has a movable lid, and right now there's a 1 kilogram weight sitting on it. If we put a 2 kilogram weight on it, that's going to cause the lid to go down. Now the volume is half a liter. So the volume has decreased by a factor of 2. The pressure increases by a factor of 2. And that's that inverse relationship. This has applications in scuba diving. For every 10 meters of depth that a diver goes down, you experience about 1 additional atmosphere of pressure because of the weight of the water. So if we've got a diver down here at 20 meters, he's experiencing approximately 3 atmospheres of pressure. So he goes down 10 meters. Up at the top, at 0 meters, he's got 1 atmosphere of pressure. Go down 10 meters, you've got 2 atmospheres of pressure. You go down 20 meters, you've got 3 atmospheres of pressure. So you need to be able, start over. There's a reason they make you take all those classes. I've never been interested in this because I'm a little bit claustrophobic, and the idea of going that far below the surface of the water is just not appealing to me. But I am aware that in order to go scuba diving, there's a lot of classes you have to take, and you have to get certified and all of this stuff, and it just seems like a lot of work, right? There's a reason, though, because you have to understand some of these principles, or you're likely to kill yourself. So if you were diving down to 20 meters, and you hold your breath as you rise up, the pressure on your lungs from the outside goes from 3 atmospheres to 1 atmosphere. It decreases by a factor of 3. If you're holding your breath, the gas in your lungs is going to expand by a factor of 3. Your lungs were not designed to do that. That's going to cause significant damage to your internal organs if that happens. And so divers are taught to always exhale as they rise to the surface. So let's do this problem and then we'll call it a day. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at that depth is 7.5 milliliters. What is the pressure at that depth? And then a second question, if the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? Let's deal with the first question first. So some of you aren't going to take kindly to this. There's a lot of story problems, word problems with gases.
But you just find the P1, V1, P1.
Yeah, you just have to identify the variables and plug them into the equations. And so it's really, if you can get over all the words, it's not that bad. So what we're going to do is we're going to take these numbers and pull them out and identify them. So I'm going to look at this and 16 milliliters of air. Well, milliliter is a unit of what? Volume. So that's a volume. So what I encourage you to do is make a table. Most of these are going to be situations where we have things changing. There's going to be a situation 1 and a situation 2. So 16 milliliters, that's the first number I come to, so I'm going to put that in a table. I'm going to say, okay, that's condition 1. We're starting there. 16 milliliters, that's a volume, so I'm going to label the column as volume. The next number I come to is 1 atmosphere. It even says the pressure is 1 atmosphere. So 16 milliliters at the surface where the pressure is 1 atmosphere. Those two numbers go together. So I'm going to write those in row 1. So I've got 1 atmosphere, and that's the pressure. The snorkeler takes the syringe from the surface and takes it down under the water. The next number we come to is the volume at this depth is 7.5 milliliters. So there's the volume. This is the other condition, 7.5 milliliters. And now there's 1 empty square in my table. That's what we're solving for. And the question is, what is the pressure at this depth? So this is what I'm trying to find, that P. I'm going to call that P2 because it's pressure at the second set of conditions. So any questions how I did that? If you call the ones on the bottom 1 and these on the top 2, that doesn't matter as long as you get them paired correctly. So I look at this table and I see I have volume and pressure, and so I'm going to use Boyle's law, P1V1 equals P2V2. I am not ever going to say, what is Boyle's law on a test? I like to give him credit for this discovery, but I don't think there's any point in making you memorize which law came from Robert Boyle, so don't worry about that. So here's the equation. We should memorize that. And we're going to solve for P2. So that means we need to rearrange the equation so that P2 is all by itself. So here's a little bit of algebra. If I want to get P2 by itself, I need to get rid of V2. So when I divide by V2, the V's cancel out. If I do it to one side, I have to do it to the other side. Otherwise, it's no longer equal. If you have trouble rearranging equations, please come see me, and I'll help you until they make sense to you. Be careful when you're copying these down. It's really easy to mess up the ones and the twos, and that'll get you the wrong answer. So there's my equation. I've got my numbers all organized here. All I have to do then is plug them in. So the volume and the pressure at the first set of conditions. Well, the pressure was 1 atmosphere. Always include the units. The volume is 16 milliliters. And then we're dividing by the volume at the second set of conditions, 7.5 milliliters. So I've got 1 times 16 divided by 7.5. So the pressure there is 2.1 atmospheres. When I look at these units, milliliters cancel out, and I'm left with a unit of atmosphere. I rounded it to 2 significant figures because all of these numbers have 2 sig figs. So that's the answer to the first question. Do you guys have any questions? The second question, if the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? Just over 10 meters, right? So he would be just over 10 meters. We could solve that more exactly. We could say, okay, the amount of pressure increase that he's experienced is, he's at 2.1 now, he was at 1.0. And so the difference is 1.1 atmospheres. And so we've got 1.1 atmospheres, and it's 10 meters for every additional atmosphere. And so that's how the guy in the back came up with 11 meters. Any questions? And we'll save Charles' Law for Thursday.